Hello everyone, welcome back to another video in the neural network series. Today we'll be programming a method to handle the forward propagation aspect of our neural network as well as our activation functions. Forward propagation is really the main way that our neural network processes information. When you give a neural network certain inputs, these inputs are then passed in through the network's layers where basic operations are performed on them. These operations are all handled with matrices and obviously our activation functions. If you'd like to know more about the math behind these operations, I have linked a good resource in the description. Okay, so let's jump into the code now. We'll begin by writing one useful function in our layer class, which will allow us to call our layers as functions. This is the built-in call method in the Python, and we write it as such, surrounded by double underscores. The function will take in self and a vector of inputs, which we will call x. Then we will simply return our weight matrix, self.weights, multiplied by this vector x, and then add it to the bias vectors, self.biases. All right, cool. Now let's move on to the activation functions, and then we'll be ready to make a forward propagation method. There are many different ways you can choose to organize your activation functions. Generally, it is a good idea to make a class that will hold all your activation functions in the same place. In this series, I will mainly be utilizing the ReLU activation function, which is the rectified linear unit, but I encourage you to try using different activation functions if you'd like, such as the sigmoid or hyperbolic tangent functions. The ReLU is a pretty popular choice, mostly because it's a pretty straightforward piecewise function that returns the value passed into it as long as it is positive. Otherwise, if it's a negative value, it will just return 0. We will achieve this behavior with the NumPy vectorized maximum function that basically just returns the max of whatever two inputs you put in it. So in this case, 0 and z. I'm using z here just because it's common notation for the pre-activated values. Alright, so we will modify this class a little bit more in the next video, but for now we're good to move on to the forward propagation function. In my network class, I will call this function forward, and it will take in arguments self and x, which will be a row vector. Next, I will initialize an activation object, which will allow us to call the ReLU function we just made. Then our first input, which is x, is going to be passed into our first layer. And I'm going to call this self.z1. And because of the call method we just wrote, we can call our first layer using the function notation, which is really nice. Then we can go ahead and activate this value. So self.a1 for activated value, and we're going to do f.ReLU to call the ReLU activation function we just made, and in parentheses I'll put self.z1. Cool. Now we literally just repeat this for all the layers. So for the second layer, I will do self.z2, and we will then pass in the activated values of the previous layer into the next layer. So self.l2 and in parentheses self.a1. And then again, I will activate these with self.a2 equals f.ReLU self.z2. Nice. So with that, we have a forward propagation method. As you can see, for the final output, I called it self.output instead of self.z or a. And also, I did not use the activation function for the output value, but you can feel free to try that and see what happens. It's usually not conventional. Okay, now we can go ahead and test this. Before we do that, as a quick disclaimer, the way we have coded this is that all inputs x are going to be a row vector. This will make passing in values in bulk down the line a lot easier, but just be careful if you're trying to plug things in and they're not and they're giving you a dimension mismatch error. Okay, so I'm going to go ahead and pass in x values. These are x values we created in the very first video of the series, and I'm also going to reshape them as a row vector because of the reason I just stated. And if we go ahead and plot this, you can see we get a pretty abysmal output. And that's mostly because this neural network is untrained and the weights and the biases are kind of just random. So in the next video, we will go ahead and actually code a backpropagation algorithm, which will allow us to adjust the weights and the biases to make a trained neural network. And this neural network will then actually be able to fit to the parabola, which was the original goal of this entire series. That was all for today, and I'll see you next time.